Once again, good afternoon, everyone. So for this afternoon is we will be discussing all about capacitors as well as the capacitance or how to measure the capacitance of a capacitor. So when we define capacitor or capacitors, this is a device that stores electrical charge. So we have here an example of what a capacitor uh, looks like. So any two conductors separated by an insulator or a vacuum forms a what we call again the capacitor. So again, this is a device that stores electrical charge. So in circuit diagrams, a capacitor is represented by either of these symbols. So as you can see, we have this one, two parallel lines. So the symbol, the vertical lines na symbol, it's either straight or curved. It represents the conductors. So this two here, this represents the conductors. While the horizontal lines, this one and this one, they represent the wires that is connected to either conductor. So this one, again, these two horizontal lines, these are, or they represent the wires. So again, the two vertical lines or one vertical line and a curve, a vertical nga curve, they are the conductors, while the horizontal lines or the two horizontal lines represents the wires that are connected to either of these conductors. Okay. So now, how about the capacitance? So si capacitance is the measure or a measure of the ability of a capacitor to store energy. So we have here the symbol for capacitance, capital letter C. So capacitance is equal, or C is equal to, we have here Q. Q is our charge. So again, this is the capacitance. And we have this one right here, VAB, is our potential difference. So we have discussed last meeting all about the potential difference, or the voltage from points A to B, or like B to A. So this is the potential difference between the capacitors. So this is how we would measure or how we would solve for the capacitance of a capacitor. So again, C is equal to Q divided by VAB, or the potential difference. So how about the unit of the capacitance? So the unit for capacitance is farad, or farads if plural, and then it has a symbol of capital letter F. So 1 farad is equal to 1 coulomb per volt, or 1 coulomb over 1 volt, because again, the unit for charge is in terms of coulomb or coulombs, and then the charge, the unit for the potential difference is in terms of volt or volts. So again, 1 farad is equal to 1 coulomb per volt, or 1 coulomb over 1 volt. Okay, so how about capacitors in a vacuum? So for capacitors in a vacuum, we have this, or the best example for a capacitors in vacuum is a charged parallel plate capacitor. So we have the figure, in figure 24.2, this is an example of a parallel plate capacitor. So to solve for the capacitors in vacuum, we have, this is the formula for the capacitance. Again, capacitance is equal to the charge Q divided by the potential difference VAB. So given the area of the parallel plate and the distance D between these two parallel plates, we have to solve for the capacitors in a vacuum, it is equal to, we have here epsilon naught. So this one is epsilon naught, which is the permittivity of free space, or what we also known as the electric constant. So the value of epsilon naught is, we have here 8.854 times 10 to the power of negative 12 farad per meter. So mo na siya unit ay value ni epsilon naught, or again the electric constant or permittivity of free space constant. So again, to solve for the capacitors in vacuum, we have C is equal to epsilon naught times, we have the area of this parallel plate capacitor, divided by D, which is the distance between these two plates. Let's say plate A and plate B. Okay. So, let's, the unit for the capacitor in terms of the area and the distance between two plates is, we have here 1 farad is equal to 1 coulomb squared per Newton times meter, or we have 1 coulomb squared per joules. So, again, the unit for capacitor, capacitance, is still farad. But in capacitors in vacuum, mo ni ang ato ang unit. But still, again, it is just equal to farad. So, again, 1 farad is equal to, or equivalent to 1 coulomb squared per joules. Okay, di ba si joules is in terms of Newton times meter. So, again, this is the equivalent of the unit farad in terms of coulomb and joules. Okay, so we have here, for our first example, the parallel plates of a 1 farad capacitor are 1 millimeter apart. So the question here is, what is their area? So this is an example of a parallel plate capacitor. So the given values are, we have the capacitance of a capacitor, which is equal to 1 farad, and also the distance between these two parallel plates, which is 1 millimeter. So 1 millimeter, when we convert that into meters, so diba 1 millimeter, 1 meter is equal to 1,000 millimeters. Okay, so now 1 millimeter in terms of meter is equal to 1 times 10 to the power of negative 3 meter. So that is the value of the distance between the two parallel plates in terms of meter. So now, to solve for the area, diba, we have this equation for the capacitance. Capacitance is equal to the permittivity of free space constant, epsilon naught, times, we have here, the area divided by the distance. So to solve for the area, we need to multiply both sides with D, so that the D here will be cancelled out. So we have C times D is equal to epsilon naught times the area. Okay, so the next is to divide both sides with epsilon naught, so that ang mabili na lang sa right side sa equation will be the area, which is what we are looking for. So, to solve for the area, it is equal to the capacitance times the distance divided by epsilon naught. So by the way, again, the value of epsilon naught, since it is a constant value, it is 8.854 times 10 to the power of negative 12 farad per meter. Okay, so we have naman tayo value ni capacitance as well as the distance and also ni epsilon naught. So we can solve now for the area. Okay, so we have here C is 1 farad times the distance, which is 1 times 10 to the power of negative 3 meter, divided by the epsilon naught, which is 8.854 times 10 to the power of negative 12 farads per meter. Okay, so as you can see here, okay, so the unit farad will be cancelled out, and then we have right here meter divided by 1 over meter. So meter divided by 1 over meter is just equal to meter squared, which is the unit for the area of the capacitor. So for the area, our unit will be in terms of square meters. Okay, so we have right here 1 times 1 times 10 to the power of 3, which is 1 times 10 to the power of 3, divided by 8.854 times 10 to the power of negative 12, which is equal to, we have 11294,3302.5 square meters, or we can also have it as 1.13 times 10 to the power of, we have positive 8 square meters. So this is the area of our parallel plate capacitor. Okay, given the capacitance, which is equal to 1 farad, and also the distance of the two parallel plates, which is 1 millimeter apart. Okay, so that is for our first example, or our example number 1. Okay, now, so we go to our next example, second example, which is again an example of a parallel plate capacitor. So number 2, we have here the plates of a parallel plate capacitor in vacuum are 5 millimeters apart and 2 square meters in area. Okay, so let's write the given first. So we have the distance between these two parallel plate capacitor, which is 5 millimeters apart, and we have the area, which is equal to 2 square meters. Okay, so at 10 kilovolt potential difference is applied across the capacitor. So we are also given the potential difference of these two parallel plates, which is 10 kilovolts. So 10 kilovolts, it is equal to 10 kilo is in times 10 to the power of positive 3. 10 times 10 to the power of 3 volts, or we can also have it as 1 times 10 to the power of 4 volts. Okay, so compute the capacitance between the plates. So we need to compute, or we need to solve for the capacitance. So take note that the equation to solve for capacitance is, we have C is equal to epsilon naught times, we have A divided by the distance. So again, our epsilon naught is equal to 8.854 times 10 to the power of negative 12 farad per meter. Okay, so we have the value of the area as well as the distance and our epsilon naught, so we can solve for the capacitance between this parallel plate capacitor. Okay, so substituting their values, we have 8.854 times 10 to the power of negative 12 farad per meter times, we have our area is 2 square meters divided by the distance, which is, for the distance, by the way, distance is 5 millimeters. So again, 5 millimeters in terms of meters. So 5 divided by 1,000 is equal to 5 times 10 to the power of negative 3 meter. Okay, so we have our D is 5 times 10 to the power of negative 3 meter. Okay, so we have right here for the units. Now, how about for the unit? Okay, so for the unit, the 1 over meter of our epsilon naught will be cancelled out with our 1 over meter sa tuang distance. So, okay. So 1 over meter, sorry. Sayop. Okay, so 1 over meter times, we have meter squared over meter. So it becomes meter squared over meter squared, which will be cancelled out. So our unit nga mabilin is in terms of farad or farads. Okay, so let's calculate. So we have 8.854 times 10 to the power of negative 12 times, we have the area, which is 2 divided by 5 times 10 to the power of negative 3, which is equal to, so our capacitance for this parallel plates is equal to 3.5416, or we have 3.54 times 10 to the power of negative 9 farad. Or we can also have it as, take note na times 10 to the power of negative 9 is nano. So we can also write it as 3.54 nano farad. So this is our capacitance, or the value of our capacitance for these two parallel plate capacitor. Okay, so this is for our example number 2. Okay, so now we proceed with capacitors now in series and in parallel. Okay, so this is an example, figure 24.8 is an example of a series connection of these two capacitors. So this is the first capacitor here. So as you can see, we have 3 points, point A, point C in the middle, and point B here. So to solve for the potential difference from point A to point B, diba, we have VAB is equal to the potential difference from point A to point C, and plus the potential difference from point C to point B. So this is how we would solve for, okay, we have 3 points man. So if duha lang ka points, wala na ni si point C. So okay na, diretso na si VAB. But since here we have 3 points in between, point C in between of these two series nga connected nga capacitors. So to solve for the potential difference is we get the sum of the potential difference from point A to point C and the potential difference from point C to point D. So this is our first capacitor, C1, and our second nga capacitor, which is C2. So as you can see, naka-series connection siya. So to solve for the equivalent resistance, or we call it as the total resistance between this capacitance, of these two capacitors, So we have this one. Take note na, di ba, to solve for the capacitance, or the equivalent capacitance, we have our equation Q over V, or Q over VAB. But here, since VAB is equal to VAC plus VCB, so VAC here, or our V1, okay, mo man siya nga to ang potential at the first capacitor, C1, and VCB is our potential at the second capacitor, C2. So, from the equation of the capacitance, which is equal to Q over V, so to solve for the potential, so we have V is equal to Q over C. So that's why we have for VAC, our equation is Q divided by C1, which is our first capacitor, and VCB is equal to Q over C2. So if we will now add, or if we now want to get the VAB, or the potential difference from point A to point B, so it is the sum of the two potentials, V1 and V2. So V1 plus V2 is equal to Q, because gi-factor out si Q kay common siya in between V1 and V2. So we have Q times 1 over C1 plus 1 over C2. So again, we divide both sides with, so divide both sides with Q. So that's why we have this one. V over Q is now equal to, makancel out na siya. V over Q is equal to 1 over C1 plus 1 over C2. So from here, di ba, V over Q is equal to 1 over C1 plus 1 over C2. But take note na, si capacitance is equal to Q over V, which is the reciprocal of this one. So, si V over Q is the reciprocal of this one. So, si V over Q is just equal to 1 over the equivalent resistance, capacitance. So, 1 over C equivalent is just equal to 1 over C1 plus 1 over C2. So, now, if we want to get the equivalent resistance of the capacitance for capacitors in series, we have 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3 and so on. So, depende kung pila kabuok ang imong capacitors nga naka-series. So, we have here the reciprocal of the equivalent capacitance, which is 1 over C equivalent, of a series combination is equal to the sum of the reciprocals of the individual capacitances. Okay, so, kani si 1 over C equivalent, dili pa ni mao nga to ang final answer if we want to solve for the equivalent capacitance gyud. So, let's say for example, if our value of 1 over the equivalent capacitance is equal to 4 over 5, let's say 4 over 5 farad. So, to get the value for the equivalent capacitance gyud is we want to get the reciprocal of 4 over 5. So, when we say reciprocal, so our denominator now becomes the numerator and our numerator becomes the denominator if, again, we want to get the reciprocal. So, the reciprocal of 1 over C equivalent is C equivalent over 1, or just equal to C equivalent. So, the reciprocal of 4 over 5 is 5 over 4 farad. So, ang atong final answer is this one. Dili si 1 over C equivalent. So, we need to get first the reciprocal before we can, so that we can get our final answer, which is the equivalent na capacitance, or C equivalent. So again, for the capacitors in series, the reciprocal of the equivalent capacitance, or 1 over C equivalent, is just equal to the sum of the reciprocals of the individual capacitances. So let's say, for example, you have 5 capacitors na naka-series. So if 5 capacitors, so we have 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over C4 plus 1 over C5 and so on. Again, kung depende kung pila ka buok imong capacitors nga naka-series. Okay, so that is for the capacitors in series. And for the capacitors in parallel, we have the figure 24.9. This is an example of a capacitor, parallel connection between two capacitors, C1 and C2. Okay, so to solve for the capacitors in parallel, so again, di ba, we have the equations of capacitance is equal to Q over the potential difference, VAB. Okay, so to solve for the charge, we have here Q1 and Q2. So to solve for the charge Q1, so we multiply both sides with VAB. So we have Q now is equal to C times the potential difference. So to solve for Q1, so Q1 is equal to the first capacitor, C1, times VAB. And for Q2, we have C2 times VAB. Kay the potential difference from point A to point B for these two capacitors are the same. So from point A to point B, again, the capacitors have the same potential. So ang mag-change lang ani is the value of the capacitance and the charge, Q1 and Q2. So now if we get the sum of these two charges, so let's say we have Q total, it's equal to Q1 plus Q2. So Q1 again is C1 times VAB plus Q2 is C2 times VAB. Now take note na we have a common variable, which is the potential difference, VAB. So we will factor this out. So VAB times, we have C1 plus C2. So this is now our Q total. So now, dividing both sides with the potential difference, VAB. So makancel out na siya. So we have Q over VAB is equal to the sum of these two the sum of the capacitances of these two capacitors. So now take note na Q divided by VAB is just the capacitance. So Q total man siya. So this one right here is our equivalent na, or the total capacitance, or the equivalent capacitance. We can also call it as total capacitance. So the total capacitance or the equivalent capacitance is equal to the sum of C1 and C2. So for the parallel capacitors in parallel, ang equation lang niya to solve for the equivalent or total capacitance between kung duha ka capacitors, so it is the sum of the individual capacitances. So again, this is the equation to solve for the equivalent or total capacitance for the capacitors nga naka-parallel connection. So again, the equivalent capacitance, which is C equivalent, of a parallel combination is equal to the sum of the individual capacitances. So again, we have the dot here, depende kung pila ka buok ang capacitors nga naka-parallel. So if you have again 10 ka capacitors nga naka-parallel, so we just add to solve for the equivalent capacitance. We just need the sum of their individual capacitances. So like C1 plus C2 plus C3 plus C4 up to plus C10. Again, depending kung pila ka buok ang imong capacitors nga nakaparallel. So in this case, if duha lang ka capacitors, so we have to get the total or the equivalent capacitance. So we just get the sum of the capacitance of C1 and C2. Okay. So we have here example for the capacitance in series, capacitors in series and parallel. So let C1 be equal to 6 microfarad, C2 is equal to 3 microfarad, and we have the potential difference of 18 volts. So find the equivalent capacitance, or again the total capacitance, and the charge in potential difference for each capacitor. When the capacitors are connected, we have letter A in series and in parallel. So again, we need to find the equivalent capacitance, and then we have the charge and the potential difference for each capacitor. Kay duha raman kabok atong capacitor, if our capacitors are connected, A in series and B is in parallel. Okay, so given we have C1 is equal to 6 microfarad, C2 is 3 microfarad. So 6 microfarad is 6 times 10 to the power of negative 6 farad. And 3 microfarad is 3 times 10 to the power of negative 6 farad. And then we also have VAB, which is equal to 18 volts. Okay, so for letter A is if our capacitors are in series. So meaning, to get the equivalent capacitance, we have 1 over C equivalent is equal to 1 over C1 plus 1 over C2. So we have 1 over 6 times 10 to the power of negative 6 farad plus 1 over 3 times 10 to the power of negative 6 farad. So if we want to get the sum, we have 1 over 6 times 10 to the power of 6 plus 1 over 3 times 10 to the power of negative 6. It is equal to 500,000. So C1 over C equivalent, 1 over C equivalent is equal to equal to 500,000 farads. So 1 over C equivalent pa na siya, dili pa ni mao ang equivalent gyud nga capacitance. So to get the equivalent capacitance is we need to get the reciprocal of 500,000, which is 1 over 500,000. So 1 divided by 500,000 is equal to 2 times 10 to the power of negative 6 farad, or we can also have it as 2 microfarad. So again, this is if our two capacitors are in series. So let's start with letter B sa kung sa nato si equivalent capacitance in parallel. So for parallel, we have to get the equivalent capacitance. It is the sum of C1 and C2. So C1 is 6 times 10 to the power of negative 6 farad times 3 times, I'm sorry, plus 3 plus 3 times 10 to the power of negative 6 farad. Okay, so the equivalent capacitance is plus 3 times 10 to the power of negative 6. It is equal to 9 times 10 to the power of negative 6 farad, or we can also have it as 9 microfarad. So this is our equivalent capacitance in parallel, and also our equivalent capacitance in series is 2 microfarad. So again, we are done solving for the equivalent capacitance. Now we proceed to the charge. Okay. So sa letter A sa ta, letter A. But this is for the charge. Kato ganina is capacitance. So for letter A again is in series. So for series, the charge on each capacitor is the same. Okay, so now for series again, diba, C is equal to Q divided by VAB. So to solve for Q, we need to just multiply both sides with VAB para ma-cancel out na siya. So we have Q is equal to C equivalent, okay, C equivalent times VAB. Okay, so now we have C equivalent sa itong previous na gi-solve is 2 microfarads. So we have 2 times 10 to the power of negative 6 farad times VAB is 18 volts. So Q is, okay, so let's calculate. 2 times 10 to the power of negative 6 times 18 is equal to, we have 3.6 times 10 to the power of negative 5. So again, the charge, the unit for charge is in terms of coulomb. So, for series, our charge for these two capacitors are the same. So for C1, our charge is 3.6 times 10 to the power of negative 5. And for C2, it is still the same. So the charge of C2 is still equal to 3.6 times 10 to the power of negative 5 coulomb. Okay. So how about for parallel? So for letter B, parallel. So again, this is for the charge. Okay, charge is at ta. Okay, so for parallel nga combination, Q1 and Q2 are not the same, or dili sila pareho og value. But the potential difference across each of these capacitors are the same, which is again 18 volts. So to solve for the capacitance, the charge Q1 on the first capacitor C1, so again we will be using this one, Q is equal to C times V, but this time we will be using the individual capacitances, dili si equivalent capacitance, pareha kay, unlike kay series. So Q1 is equal to C1 times V, which is equal to, we have C1 is 6 times 10 to the power of negative 6 farad times V is 18 volts. So Q1 is equal to, okay, let's calculate, 6 times 10 to the power of negative 6 times 18 is equal to 1 1.08 times 10 to the power of negative 4. And again, our unit will be in terms of coulomb. And for Q2, or the second charge, we have is equal to the second capacitor, or the capacitance of the second capacitor, which is C2, times V. So we have 3 times 10 to the power of negative 6 farad times 18 volts. So we have, again, 3 times 10 to the power of negative 6 times 18 is equal to 5.4 times 10 to the power of negative 5 coulomb. So this is our charges, Q1 and Q2, for our capacitors are in parallel. So if in series, Q1 and Q2 are the same, which is again 3.6 times 10 to the power of negative 5 coulomb. And if our capacitors are in parallel, Q1 is equal to 1.08 times 10 to the power of negative 4, and Q2 is equal to 5.4 times 10 to the power of negative 5. Okay, so now we are done with solving for the equivalent capacitance as well as the charge. So now we will proceed with the potential difference for each capacitor. Now take note na in parallel, ang potential difference of these two capacitors, if nakaparallel, is just, so for the potential difference, so ano na siya? The potential difference, if our capacitors are in parallel, the potential difference is for C1 and C2 are the same. Meaning, the potential difference for C1 or V1 is equal to the potential difference of C2 or V2, which is CVAB or 18 volts. So again, this is for parallel. But if naka-series, okay? So if naka-series siya, what we will do is okay? So if naka-series siya, so this is the potential, sorry. So for the potential difference, so again, for letter A, the potential difference will be, so again, we have our general equation for capacitance, which is C is equal to Q over V. So to solve for V, we have V is equal to Q over C. Okay, we need to multiply both sides with V and then again divide both sides with C so we can get the potential difference. Again, so for series, so V AC, so ang ato ang gibasihan aning figure is this figure right here for the series, which is we have point A, point B, and point C. So point C is in the middle of the two capacitors. So we will be using this one. Okay. So balik ta. So VAC is equal to, or our V1, or the potential difference at for the first capacitor is equal to, we have Q over C1. So we have our Q, sa atong first na dissolve, our Q is equal to, pinagamit to, 2 times 10 to the power of negative 6 times 18. So our Q is equal to 3.6 times 10 to the power of negative 5 coulomb. So muna itong gisolve kaganina. So we have 3.6 times 10 to the power of negative 5 coulomb divided by our C1, which is 6 microfarad, or 6 times 10 to the power of negative 6 farad. Okay, so we have 3.6 times 10 to the power of negative 5 divided by 6 times 10 to the power of negative 6, which is equal to 6 volts. And for VCB, or our V2, is equal to Q divided by C2, which is equal to, again, 3.6 times 10 to the power of negative 5 coulomb divided by 6, no, it's not 6, it's 3. 3 times 10 to the power of negative 6 farad. Okay, so we have 3.6 times 10 to the power of negative 5 divided by 3 times 10 to the power of negative 6, which is equal to 12 volts. Okay, so this is our potential difference across each capacitor if our capacitors are connected in series. So for the potential difference across C1, or our first capacitor, is equal to 6 volts, and our potential across C2 is equal to 12 volts. So again, that is for the potential difference for each capacitor. So again, in parallel, si V1 is just equal to V2, which is our potential difference VAB, which is equal to 18 volts. So the potential difference across these two capacitors, if our capacitors are in parallel, is just the same for these two capacitors, which is 18 volts. So this is how we would solve for the equivalent capacitance, the charge, as well as the potential difference if our capacitors were connected in series and in parallel. Okay, so that's for example number 1. Okay, so now how about for example number 2? Example number 2 is to find the equivalent capacitance of this 5 capacitor network shown. So this is letter A. Mao niya nga atong original nga 5 capacitor network. This one right here. Kana siya. Okay, so as you can see, it is a combination of a series and parallel nga capacitors. So from point A to point B. So equivalent capacitance lang atong pangitaon. Okay. So now, the first step is to determine kung kinsa ang capacitors na naka-series and kung kinsa ang capacitors na naka-parallel. So as you can see here, kanina sa blue, naka-blue nga square, these two capacitors are in series. So what we need to do is we need to get their equivalent capacitance first para if we simplify the network or the circuit, it becomes like this in letter B. Okay, so it starts with this one. So, series man ta, so 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2. So, let's have this one as our C1 and this one as our C2. So, what we have 1 over 12 microfarads, or 12 times 10 to the power of negative 6 farad, plus we have 1 over 6 times 10 to the power of negative 6 farad. So, let's calculate 1 over 12 times 10 to the power of negative 6 plus 1 over 6 times 10 to the power of negative 6, which is equal to 250,000 farad. So again, this is 1 over the equivalent capacitance. So to solve for the equivalent capacitance, we need to get the reciprocal of 250,000 farads, or we have 1 over 250,000. So 1 divided by 250,000 is equal to 4 times 10 to the power of negative 6 farad, or we can also have it as 4 microfarad. So this is our for letter A na ni siya. This is for letter A. So we have our equivalent capacitance for this one, which is equal to 4 microfarad, which is here. Okay. So now, as you can see, these 3 capacitors, can you see 3 microfarad, 11 microfarad, and 4 microfarad are in parallel, or they are connected in parallel. So for letter B is we need to get the equivalent capacitance of these 3 capacitors nga nakaparallel. So equivalent capacitance in parallel is just the sum of the individual capacitors. So let's have it as C1 plus C2 plus C3. So we have, let's have it as our C1, this is our C2, and this is our C3. Okay, so we have 3 microfarads, or 3 times 10 to the power of negative 6 farad, plus we have 11 times 10 to the power of negative 6 farad, plus we have 4 times 10 to the power of negative 6 farad. So the equivalent capacitance of these 3 capacitors is, so let's calculate again. We have 3 times 10 to the power of negative 6 plus 11 times 10 to the power of negative 6 plus 4 times 10 to the power of negative 6, which is equal to 1.8 times 10 to the power of negative 5 farad, or if we will have it in terms of microfarad, so it becomes 18 times 10 to the power of negative 6. So we move the decimal here to add another one sa to ang exponent. So we have 18 times 10 to the power of negative 6 farad, or we have 18 microfarad, which is this one. So kaning sa letter C, muna ni siya ang katong sum, or the equivalent capacitance of these 3 capacitors na nakaparallel. So again, if we will redraw our 5 capacitor network, duha na lang ang nabilin. Kaya ito naman gisimplify ang uban. So, we are left with 2 capacitors na lang, which is the 18 microfarads. 18 microfarad, which is the total or the equivalent of these 3 parallel nga capacitors. And then, we have another 9 microfarad below. So, now, kani siya nga circuit is in series na. So, from point A to point B, naka-series na ang duha. So, we have for letter C, to get the equivalent capacitance of these 2 capacitors. So, let's have this one as C1 and C2. So, we have 1 over C equivalent is equal to 1 over C1 plus 1 over C2. Okay. So, we have 1 over C1 is 18 times 10 to the power of negative 6 farad plus 1 over 9 times 10 to the power of negative 6 farad. So, we have 1 over 18 times 10 to the power of negative 6 plus 1 over 9 times 10 to the power of negative 6, which is equal to 166,666.67 farad. So again, this is 1 over C equivalent. So to get the equivalent capacitance is we need to get the reciprocal of this one. We have 1 over 166,666.67 farad. So we have 5.999. So we have 5.9999998 times 10 to the power of negative 6, or we can also have it as 6 times 10 to the power of negative 6 farad, or we have 6 microfarad, which is here in letter D. So this is the equivalent capacitance of this 5 capacitor network. So this will be our final answer na gyud. So the total or the equivalent capacitance from here, from this 5 capacitor network, we simplified it to only one, which is the equivalent capacitance of 6 microfarad. So that is how you would solve for the equivalent capacitance given the combination between series and parallel connections of the capacitor. So from letter A, we simplified the network to letter B, then to letter C, until we arrived with our equivalent capacitance or the total capacitance, which is equal to 6 microfarad. So that is for our discussion all about, again, the capacitors and the capacitance in series and parallel.